Hello everyone. Have you ever looked up at the night sky and wondered, is the universe, where the stars shimmer in silence, truly silent? Our world is constantly changing. Day turns to night, spring turns to summer, joy fades into sorrow. Everything moves. But what about the universe? For thousands of years, we believed the sky was a still dome, that stars were fixed and eternal, and the cosmos was a perfect machine, cold, unmoving, and timeless. But the truth is, the universe is not still. In the early 20th century, as science developed the tools to peer farther into space, we were shocked to discover the universe is expanding. Galaxies aren't standing still. They're moving away from each other, and not slowly, but faster and faster over time. From the Big Bang, space has been stretching, not like blowing up a balloon, but more like the distances themselves growing. The universe isn't just expanding, it's accelerating. This realization raised haunting questions. Will the universe expand forever? Will it collapse back on itself? Is there a limit to this expansion? And if so, how can we calculate it? All these questions revolve around a simple but profound concept in cosmology: critical density. In this video, we'll explore the fascinating nature of cosmic expansion, decode the idea of critical density, and discover why the fate of the universe may hinge on a number smaller than the mass of a single hydrogen atom per cubic meter. Was the universe ever still? There was a time when people believed the universe was motionless, when Galileo first pointed his telescope to the stars, when Newton wrote the laws of gravity. Even Einstein, in his first version of general relativity, added a cosmological constant to force the universe to stay still, because he couldn't accept that it might be expanding. But the truth didn't stay hidden for long. Einstein's theory of relativity, published in 1915, showed that space and time are connected, a dynamic fabric that bends and shifts with mass and energy. This meant the universe couldn't be static. And in 1929, Edwin Hubble provided the proof. Using a telescope at Mount Wilson, he observed galaxies drifting away, not just some, but all of them. And the farther away they were, the faster they moved. The universe was expanding. That became the new truth. At first, scientists believed expansion would slow down, perhaps even reverse into a big crunch. But with new instruments, Hubble, James Webb, Planck, WMAP, we learned something stranger. The universe isn't just expanding, it's expanding faster and faster. What could possibly cause this? It all begins with a key idea: critical density. Measuring expansion, the Hubble constant. When Hubble published his discovery, he also gave us a way to measure the universe's expansion. By observing galaxies and measuring their redshift, the stretching of light as objects move away, he found v equal h0x d, v, velocity of a galaxy moving away, d, its distance from Earth, h0, the Hubble constant, the current rate of expansion. Sounds simple, right? But determining the value of h0 has sparked decades of debate. Using early universe data, like CMB from Planck, h0 67.4 km/MPC. Using local data, like supernovae, h0 73.2 km/MPC. This disagreement is known as the Hubble tension, and it remains unsolved. But either way, one thing is clear. The universe is expanding at a tremendous speed. 1 megaparsec equals 3.26 million light-years. So for every 3.26 million light-years, space expands by about 70 kilometers every second. At cosmic scales, that adds up to regions of space moving apart faster than light. And no, this doesn't break relativity, because space itself is expanding. Critical density, the balance point of the universe. The key to understanding the universe's fate isn't just how fast it expands, it's how heavy it is. More specifically, does the total mass energy density of the universe exceed, equal, or fall short of the critical density? Critical density is the perfect balance point where Gravity tries to pull everything together. Expansion tries to push everything apart. If actual density, critical, the universe will eventually collapse, big crunch. If actual density equals critical, expansion will slow down but never stop. If actual density, critical, the universe will expand forever, accelerating. Using Einstein's equations and the Friedmann model, RC equals 3πxHO2, 8 pg. RC, critical density. H0, Hubble constant. G, gravitational constant. Using H0, 70 km/s MPC, RC, 9.23, 10 to 27 km3. That's about the mass of 5.5 hydrogen atoms per cubic meter of space. What is the universe's actual density? Modern surveys show the universe's energy budget is 5% normal baryonic matter, 27% dark matter, 68% dark energy. Combined, the actual density is 8.5 × 10 to 27 km3, about 92% of critical density. This tells us the universe will expand forever and keep accelerating. Galaxies will drift apart. Darkness will grow. Eventually, everything will become invisible, unreachable. No big crunch, no cosmic rebirth, just cold, endless expansion. Why is the expansion accelerating? Enter dark energy. Imagine throwing a ball upward. Gravity slows it down, eventually pulling it back. Scientists once thought the universe would do the same, slow down after the Big Bang. But instead, it's speeding up. The engine? Dark energy. It's invisible. It doesn't shine, reflect, or absorb light. It doesn't interact with matter the way we know. But it fills the universe and pushes space to expand faster and faster. We know it exists because we see its effects. Galaxies accelerating apart. Models only work when dark energy is included. Confirmed by Type Ia supernovae, CMB data, Planck, WMF. Dark energy has negative pressure. It doesn't pull things together. It pushes them apart. And the more space there is, the more dark energy, fueling a feedback loop of eternal expansion. How will it all end? Depending on dark energy's nature, we face three possible fates. The big freeze, stars burn out, matter dissolves, the universe fades into cold darkness. The big rip. Expansion accelerates infinitely, even atoms are torn apart. Space and time unravel. The big crunch, big bounce, only possible if density. Critical data says very unlikely. In short, dark energy is reshaping the universe's destiny, silently steering galaxies, stars, and even us toward an unknown future. When you look up at the night sky, you might think the universe is frozen in place, like a painting on the wall. But it's not. It's moving, expanding, changing. Together, we've explored the shift from static models to the Big Bang, the concept of critical density, the numbers that define cosmic balance, the force, dark energy, that rules our future. What matters is not just the facts, but the spirit of inquiry. We live in a vast, mysterious universe, and instead of being discouraged, we should be amazed that in this sea of stars we can ask, measure, reason, and learn. The universe may end in cold silence, but until then, we, the small, thinking beings, can still light the way with knowledge. What do you think about an ever-expanding universe? Should we fear it, or keep looking up and asking more? Share your thoughts in the comments below. And don't forget to subscribe, like, and hit the bell, so you won't miss the next video as we continue exploring the deepest mysteries of the cosmos. See you in the next one, and have a beautiful day.